So we will begin this day with our very own past student or postdoc fellow at CAM, Ameya Jagtap. He is currently holding a position of assistant professor at applied mathematics at Brown University. And he will be telling us about physics-informed neural networks, a new paradigm for learning physical laws. Ameya.
Yeah, thank you, Srikar, for the nice introduction. And yeah, today I'll be presenting the my topic of presentation is this physics-informed neural network, a new paradigm for learning physical law. So basically, I'll explain about how to solve the inverse problem using machine learning. So before we start, so as we know, we organized this conference in the memory of Professor Vasudeva Murthy, sir. So I worked under him for almost 2.5 years. And I guess I was his last postdoctoral student. I'm not sure whether he has taken after that or not. During that time, I learned a lot of things from him, not just academia, but also about life. He was always passionate about teaching as well as research. And in fact, just 3 weeks before his demise, we were planning about the series of lectures on scientific machine learning, but unfortunately, we couldn't materialize it. So I miss him, and I'm sure his blessing will be with us always. So as he said, the show must go on. So let's move on to our today's topic. So I'm sure you all know this artificial intelligence, or in short AI, which has achieved remarkable success in both academia and industry. And it has been applied successfully in many applications like healthcare, online shopping, autonomous vehicle, stock exchange, space exploration, and even creating an artificial music, and so on. The list is long. So basically, in this talk, we are interested in the subset of an artificial intelligence, which is called as machine learning, which is the study of computer algorithm that can improve automatically through experience and by the use of data. And in particular, we are interested in the physics-informed machine learning, or in short, PIML, where we are actually enforcing the physical laws in the machine learning framework. So with this, the overview of today's talk is, so basically I'll be discussing the method called as physics-informed neural networks, or in short PINNs. So basically it's a particular case of physics-informed machine learning method. And we'll see the various application of PINNs specifically for the inverse problems, for high-speed flows, or the quantification of material properties, as well as inverse problems in nonlinear water waves, etc. And we also discuss about some of the limitations of PINNs, and we discuss how to overcome that limitation with the recent extension. The first extension is the conservative PINNs, or in short CPINNs, specifically tailored for the conservation laws. And next we will discuss more general extended PINN methods, or XPINNs, which can be applicable for any equations and not necessarily conservation laws. So traditional approaches for the scientific computations like FEM, FDM, and finite volume method, they have undergone a remarkable progress, but they still operate under very stringent requirement. So basically, they require a precise knowledge of the underlying physical laws, boundary condition, initial condition, and then they often need time-consuming workflows such as mesh generation and long-time integration. Well, on the top of this limitation, well, I'm talking about the ill-posed problems. The simulation of real observation data for ill-posed problems can become very costly, where simulation need to be performed multiple times to either discover a missing physics or calibrate the free parameters in the model. So basically, I'm talking about this region here, where we have some data available, not necessarily on the boundary or at initial condition. And at the same time, we also know some physics. Maybe we may not know exact physical laws, but part of it. And top of that, the given data could be dinky, dirty, dynamic, or even deceptive. So in this scenario, this is a highly ill-posed problem, and the traditional method, they do suffer. And physics-informed machine learning can play a bigger role for such problems. So basic question is, what is physics-informed machine learning? So basically, it's a dictionary definition here. It is a process by which the prior knowledge stemming from the observational, empirical, physical, and mathematical understanding of the underlying model can be leveraged to improve the performance of the ML algorithm. So basically, by incorporating the physics in the machine learning framework, we are trying to improve the robustness of the algorithm, machine learning algorithm, as well as the trustworthiness. Basically, when you use machine learning as a black box for scientific problem, there is no guarantee that they always give the accurate solution. So that's why we are enforcing physics, so that we can actually constrain the space of admissible solutions here. So let's see, the next question is how to make machine learning physics informed. So there are basically three ways: observational bias, inductive bias, and the learning bias. So basically, in case of observational bias, that amounts to the training of the model on the data that reflect the underlying physical principle in the first place, which require a lot of data. The inductive bias is the one that amounts for designing specialized priors and architectures such that certain physical principles are encoded inclusively in the model itself. And finally, the learning bias, where we that amounts to enforcing the physics through penalty constraint in the loss function during model training and not through the architecture of the model. So in this talk, we are actually focusing on the learning bias techniques. So this physics-informed neural networks belong to the learning bias class. So a brief literature survey. So using physics or solving the PDs using neural network is not new. The Lagares and others, they proposed this idea back in late 90s and early 2000. But recently, this idea took a lot of momentum with the work of ORD, who actually uses physics-informed machine learning for the multi-scale simulation problems. And later, Bruton and others, they proposed Cindy framework in 2016. Then Karpatne and other proposed physics-guided neural network. And there are so many work. And recently, Ricey and others, they propose PINN framework. And the list is long. So I'm basically I'm focusing on PINNs here. Okay, so before moving to PINNs, just see the what is neural networks. So we will just discuss a very basic multi-layer perceptron or feed-forward neural network. So here is the sketch here. So you can see here, this is the neural network here, where the input of the neural network is X and T, and the output of the neural network is U basically. And these are the hidden layers where the information passes, and they are equipped with all the basically tuning parameters, weights, biases, and A is the activation slope. And their job is we are to enforce the output of the neural network is equal to the given output, the target function here. And that basically gives a measurement loss. You can see here the measurement loss. It's a data mismatch loss between the output of the neural network U. So this theta tilde is basically represents all these parameters, W, B, and A. They are trainable parameters. So that's the output of the neural network. And that's the target solution here. And this is our loss function. And the optimizer's job is to minimize this loss such that the output of the neural network satisfies the data which we have in hand. So basically, it's in simple word, it's a least square regression problem here. So that's the simplest neural network which we can define. And okay, then what is physics informed neural network? So here, basically, we are not just enforcing the output of the neural network to satisfy the data, but at the same time, we are actually enforce it to satisfy the governing physical laws. So in this case, if you see, I'm just using a viscous Berger equation here, and I'm forcing my solution U, output of the neural network, to not just satisfy this target data, but at the same time, I'm enforcing it to satisfy physics. So, and how I'm doing that? I'm using automatic differentiation to find out all these derivatives in the governing equation. So that actually gives my residue loss, which I am actually adding into the loss function. So when you minimize this loss function, basically this is a surrogate model. And when you minimize this loss function, you recover the actual solution of the governing PD. So one more thing, it not only satisfies the governing PD, but it also satisfies the boundary condition and the initial condition for, of course, initial boundary value problem. Okay, so as I said, so PINN algorithm aims to learn the surrogate U, which is the output of my neural network, which satisfies both the data as well as the PDE for predicting the solution of the given PDE by minimizing the loss function. So these are the optimal set of parameters which we obtained by minimizing this loss function. And when we plug these parameters with new test data, with, of course, with fixed initial and boundary value, and of course, for the same PDE, we can recover the solution of PD here. So what's the advantage here? PINN can solve both forward problems and ill-posed inverse problem. Okay, look at this pedagogical example here. Again, I'm just using the viscous Berger equation. My X domain is from -1 to 1, and my initial condition is just a sine wave here, and my boundary conditions are 0 here. So if you see here, that's the XT domain here, and here is the exact versus predicted comparison. So prediction by the neural network, and you can see that it actually gives quite accurate results. So these are the 3 lines. You can see it here, the white lines here, where we are comparing this exact versus predicted values. And that's the loss function. So basically, I use Adam optimizer for first 100 iteration, and then I switch to LBFGS optimizer. So after 5,000 iteration, I get perfect results. It won't take much time for the small problems, but of course, for big problems, the training takes times. But now there are many variants of PINN which can actually use to reduce the computational cost here. So let's see some more scientific applications. First, we'll see the application for high-speed flow. So here, the aim is simple. Here we are solving the inverse problem to find out the gas constant gamma, and the only input we have is the Schlieren data for density gradient. You can see that we use 2 different meshes here. One is with the random points, and one where I'm actually coalescing all the points along the discontinuity. So this basically it's an oblique shock wave problem, and this is the results for given by the PINN. So I tried with the clean data. Well, the data obtained from the Schlieren, it's clean, there is no noise. And for the random points, I got actual value of gamma is 1.4, but I got 1.46. And with the clustered, I'm quite close to 1.4 here, because, you know, this orientation of shock wave plays a big role here. Even slight change in the angle of the shock wave can give you completely different solution. So that's why the clustered points are giving much better results than the this randomly chosen points. And since it's an inverse problem, we know the location of shock from the Schlieren data. And if you add noise in that data, 1% noise, 2% noise, we are still able to recover the gas constant pretty accurately in both cases. But you can see that with random points, there is a large error compared to the cluster points. Okay, let's see another example, which is the quantification of material properties.
May
so
I ask a question? Would you mind?
Yes, yeah, please go ahead.
In the previous problem,
yes.
So here, the usual inverse map is known to be like solvable and so on.
Sorry?
The usual inverse map is like a well-known solved problem.
Well, this is highly inverse problem. We do not have any data on velocities basically, and I am using some data on pressure, but it's just at single point. So that's the data we obtained from the pressure probe.
I see. And the forward map, is some sort of a some PDE, I imagine.
Yes, we do enforce the PD here.
I see. And like, is this mapping linear, non-linear, and?
It is highly non-linear because, you know, this is we are solving Euler equations here, and only data what we have is the Schlieren data, and that too the density gradient. We don't have any data on velocity or pressure or any other temperature basically.
I see. So, and when you introduce a noise, it is uniform 1% noise. Like
it's a Gaussian. It's a Gaussian noise, a random Gaussian.
I see. I understand. Okay. All right. Thank you. Ananya has raised her hand. Maybe Ananya, could you please unmute yourself and ask a question if you want to?
Good morning, sir.
Morning.
Sir, I want to know what is the meaning of shock wave here? Means what is its physical interpretation or means benefits?
Basically, this problem is we are solving a compressible fluid flow here, where shock wave appears at high speed flow, and it's basically a discontinuous features across which there is a sudden jump in all the variables like pressure, temperature, velocity, and density. So and the orientation of shock is highly depends on the nature of the type of gas which we are using. Here we are using air. So for air, the value of gas constant is 1.4, and that's the inverse problem here. We are actually finding the gas constant, or basically what's the medium. In this case, it's air, from the data obtained from the experimental setup, Schlieren data.
Thank you, sir.
You're welcome. Any other question? Okay, so let's move forward. So the next example is quantification of material properties. So you can see here, we have basically the aim is to infer the spatial variation of compliance coefficients of the material using only displacement data that is obtained from the experiment. So basically, that's the experiment, the experimental data we have, where we use the surface acoustic waves to get the displacement in X2 direction. And along with the experimental data, we also use the synthetic data, which we have generated using a 3D solver, and that gives the displacement in X1 and X3 direction. So that's how we have displacement in X1, X3, and X2 and X3 direction. And the aim is to find out what's the compliance coefficient of the material, what kind of material it is. We don't know the material, basically. So if you see this results given by PINN, so on the left-hand side, you can see the data points in red, where we know the displacement, and that's the wave, which is traveling through the material. It's 5 megahertz wave, frequency wave. And you can see the actual data in green and the PINN simulated data in dashed line with different colors, which are matching perfectly. And then it actually gives the compliance coefficient. So in this case, for single crystal nickel speed, the shear wave mode speed is 2.97 millimeter per microsecond. And that's the results which we get from PINN. So that's the second shear wave mode, you can see here. And you can see it is, it's not constant, it's spatially varying. And that's why we know the existence of polycrystalline material. So it's not made up of single crystal, nickel, but multiple polycrystals. And on the right-hand side, that's the compliance coefficient C44. And we compare the error, and it's below 1%. The error between actual value and the predicted value given by the PINN is less than 1%. So the next example is the inverse water wave problem. So basically, we are solving the Serre-Green-Nagari equations here. You can see it in this box. And we have this data. We have the eta. Eta is the surface wave height. H is the bottom topology, and U bar is the velocity. So the only value or the only experimental value which we have is the surface wave height, eta. And at discrete location, we know H values, and we do not know velocity here. So the second thing is, the only thing which we know about velocity is if there is a wall. So if there is a wall, then of course we deploy the no slip the reflecting wall boundary conditions here. So you can see here the aim is to infer the transient velocity field from the corresponding and the corresponding forces on the walls using only water column height, eta. So you can see on the right hand side, there are two results basically. So this is the result. You can see, actually it's not that visible, but you can see these dotted black lines here. So these are the wave gauges which we placed between -40 and +20. This is x-axis and this is time axis. And these are the wave gauges which gives a time series data for eta. And when we feed that data to the PINN, basically it gives U velocity, U bar, you can see that. Here we use 12 gauges and here we use 20 gauges. And that's the pointwise error. You can see that basically we also don't have full knowledge of eta. So we are also predicting eta as well as U. So we have eta only at these gauge values. We don't have in between values. So you can see the pointwise error is the maximum pointwise error is 10 to the power -2 in both cases. And well, I'm not showing here, but as we increases the number of gauges, we have seen that the error decreases in velocity. Well, now the next question is how to choose the optimal location for gauges, and that can also be done. We just need to, once we have the full information about eta, we can find out the SVD of eta and Then from the orthogonal matrix U, when you take when you do QR factorization, so the pivot values of that QR factorization basically gives the optimal gauge locations. So I'm not going into the details. You can always see this paper here. It's already published. In case if you have any question, you can ask me. So let's move on. So we have seen that PINN can successfully solve very ill-posed problem where we have limited set of data. But of course, there are certain limitations of PINNs. So the first limitation is due to high dimensional non-convex optimization problem, the accuracy of the method suffers. So basically the maximum accuracy which we obtained here is 10 to the power -6, -5. That's because you have it's highly non-convex optimization problem with thousands of parameters. And the second limitation is the large training time. So in this work, we are basically trying to mitigate this large training time. So there are classical approaches to do that. So first one is data parallel approach. You can see here on the right-hand side. So we have a big data. We split that data into small data set, D1, D2, D3, and D4, which are equal to the number of processor what we have. And we initialize a neural network model with the same parameters. So we have neural network model NN, denoted by NN, with same parameters. And since this neural network is working on different set of data, we end up with different loss function, J1, J2, J3, and J4, right? And then here they use the distributed optimizer, which average out the gradient of the loss values through all reduce operation. And this average gradient of the loss function is then sent to the all the processor through the broadcast world. And then they update the parameters W and B in the networks. But if you see that they are using a single network here. So that's one of the issue with the data parallel approach. Well, in the classical approach, they also propose model parallel. Here, instead of basically here they are splitting the data into batches B1 to B4, and every layer, in this case there are 4 layers of the neural network. Every layer is assigned as GPU, and once L1 is once B1 is processed by L1, it will pass to L2, and L1 will start working on B2. Okay, so this is basically they are finishing all this work in a pipeline approach. So that's the forward mode, and that's the backward pass. And that's how they are actually updating these weights and biases. So these are basically a parallel approaches. You can make the algorithm parallel, but okay. So our approach is the domain decomposition approach. So basically we have a domain. We split the domain into subdomains, and instead of a single pin network, we use multiple pins in each subdomain. And you can see here now again it's a pin network. We have neural network here, we have physics informed network here, and along with the PDE, we also have interface condition, which is required to stitch these subdomains together. Right. So now our loss function consists of my data mismatch term, the PDE residue, and the interface loss now. So this way, we are actually using multiple neural networks to parallelize the simulation. So what's the advantage here? Of course, parallelization capacity, which is also common for data parallel and the model parallel approaches, which I have shown earlier. But now what they don't have is the last 3 points given in the blue curve, blue color. So it's the domain decomposition approach has local representation capacity. So basically, since you are using different neural networks, we can use different depth, different width, number of neurons, number of hidden layers, and that's how we can change the representation capacity of the network. You remember that for both data and model parallel, they were using single network, not multiple networks. So they don't have this facility. Next is efficient hyperparameter adjustment. We can adjust all the parameters, hyperparameters of the network, like depth, width, learning rate, even the what kind of optimizer you want to use in a particular subdomain, and that can be done here. We have also seen that reduction in error propagation in the domain because of the additional interface condition which are defined inside the domain. So let's see what kind of condition we have here. Okay, so the first extension is the conservative pins. As I said, it is applicable for the conservation laws. So these are the interface condition. So suppose we have Q subdomains. In the QH subdomain, we have the flux interface, flux continuity, the normal flux continuity. And we are also enforcing the average solution across the interface. So basically, you can see this figure below. When we enforce the average solution continuity, when the solution is continuous, so basically it becomes a continuity of the solution condition at the interface. It is given by this the green bar here. And when the solution is discontinuous, which is possible in case of hyperbolic conservation laws, where we have shock waves, we are basically enforcing the midpoint here at the interface. Okay, so let's go back to our Viscous Berger test case. You can see here again that's the solution xt in the xt plane. I'm dividing this x plane into 4 subdomain. You can see this 4 bars here, so named numbered from bottom to top, first, second, third, and 4. And in each subdomain, I'm using these number of layers, number of neurons, residual points, and the activation function. So you can see that I'm using different number of layers here for the neural network, different number of neurons, different number of residual points, where you are evaluating the residual term, which I have shown earlier, using the automatic differentiation, and of course the activation function. And you can see the pointwise error on the right hand side figure after 15,000 iteration. So you can see this relative L2 error. So we have solved this problem without average term. So this average term, enforcing along the interface with and without average term. So basically the blue curve is without average term. So you can see that the relative L2 error stuck here because we just have flux continuity condition, but no, we are not enforcing the continuity of the solution, the average solution. So when we enforce the average solution continuity, the relative error decreases faster. It is still decreasing, but we stopped at 15,000 iterations. So that's the preliminary results. Okay, let's move on to the more complex problem where we solve the 2D incompressible flow. It's a well-known test case, lid-driven cavity. Here we divide the domain into 12 subdomains, and these are the number of layers, number of neuron and residual points in each subdomain. So basically my activation function is tan h, and the optimizer is Adam here, and the learning rate for that optimizer is 6 × 10⁻⁴. And that's the results. So I compared the predicted velocities with the GIA. That's the standard reference solution available, and they are matching perfectly. Okay, let's see the inverse problem. Okay, so in this case, I am supplying this set of equation. So you have unsteady term, you have nonlinear convection. Now you have linear convection with beta as the parameter, diffusion term nu, and dispersion term alpha. So basically our aim is to infer these quantities beta, nu, and alpha. And the data, what we have is the data obtained from Viscous-Burgess equation. So basically for Viscous-Burgess, my beta is 0, nu has some finite value, and alpha should be 0. And these are the results here. So again, we have 4 subdomain as I have shown earlier here. So I decompose the domain into 4 subdomains, and I initialize these values alpha, beta, and nu. In these subdomains, these are separate values, and you can see that as the number of iteration as the optimizer starts training the network, it actually combines together, and then it goes towards the exact value shown by this black dash line here. So you can see that once alpha and beta goes to 0, then nu actually goes towards its actual value. Otherwise, it was actually initially deviating away from the exact solution. And these are the results. So alpha exact value is 0, but of course, in a real simulation, you will never get 0. It's very small values, and the exact value for nu is 0.0031, and what I got is 0.0034, which is pretty much accurate. Okay, so what next? So domain decomposition strategy for every PD, it will be really helpful if we use this strategy for every PD, but not necessarily for the conservation laws. And of course, if it is possible, we would like to have this strategy, domain decomposition, in space and time. So the answer is XPINN here. Okay, then how you can do it? So in this case, the interface conditions are quite simple. So we again use the same average solution continuity across the interface. And now instead of enforcing the flux, we are using the continuity of the residuals. So basically we are enforcing the residual of the governing PDs directly across the interface. And that's the that way you can actually decompose both in space and time. And apart from that, if you have additional continuity conditions, like if you have any integral constraint or any other higher order derivative continuity condition, you can also enforce that one. What's the advantage? We can extend the CPINN strategy, XPINN strategy for any differential equations instead of just a conservation loss. You can decompose in space and time. And the interface conditions are simple in terms of implementation, basically. So when you have flux continuity condition, normal flux continuity condition, you need to always find out the normal direction of the flux. But here we are enforcing the residual continuity condition, so we don't need the direction. So in that sense, it's very simple to apply these interface conditions. Okay, so what's the that's the comparison between PINN, CPINN, and XPINN. We have special, we can decompose in space, yes, for CPINN, XPINN, but not for PINN. We have parallelization capacity for CPINN, XPINN, yes. Local representation capacity, yes. We can efficiently adjust all the hyperparameters for both CPINN and XPINN. Applicability. For CPINN, it's just a conservation loss, but for XPINN is any PD, just like PINN. Interface conditions are simple in case of XPINN compared to CPINN. And of course, we can also decompose in space. So XPINN is a more general approach compared to CPINN, and more advanced than the vanilla original PINN. Again, let's come back to the, how much time do I have? I'll just quickly finish this. So let's come back to the Viscous-Burgess equation. Now you can see the decomposition here. We have a dolphin and the outside blue water. So we have just 2 subdomains. And now remember, this is the XT domain, basically. So you can split it into any way, no matter what's the shape of the interface. And that's the exact versus predicted solution. So you can see easily we can get the quite accurate solution. My L2 error is in the range of -3 here, -2 basically. Okay, we have also done parallel implementation here, but I'm not sure how much time do I have.
We were already running out of time, I guess.
Okay, then, this is the reference for
3 minutes, maybe.
Sorry?
You can perhaps take 2 or 3 minutes.
Okay. No, I'll just finish this one. So we have done the parallel implementation of CPINN XPINN, and I'll just show you some main results. So that's the speed up which we obtained with CPINN. It's almost linear, and it's slightly sublinear for XPINN. Because in CPINN we are just enforcing the flux continuity instead of the residual continuity in XPINN. And if you see the efficiency, we are almost hitting 80% for CPINN and 70% for XPINN. We also developed theory for XPINN. It's under review. One with Professor Kawaguchi. He's from MIT. Now he's at National University of Singapore, and one with Professor Siddharth Mishra. You all know him very well. And that's the conclusion. So basically, we presented the physics-informed machine learning method, in particular PINNs, physics-informed neural network. We have also seen some of the applications of PINNs for inverse problems, and we try to mitigate the limitations of PINN by defining both CPINN and XPINN methodologies, which can be easily parallelized, and there are so many advantages, and they both map implicitly on distributed heterogeneous computing environment, CPU, GPU. You can see the reference, and they're very computationally efficient, and that's the promising approach for solving large scale and high dimensional problems. So if you have questions, I'll be happy to answer.